Hello and welcome to the web series, ZeroPM Pieces. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
So the topic of the presentation is called the wet pyrolysis. It was a very interesting term that we received, I think, from Hans-Peter to talk about, because it's actually what is the truth. It's what is happening, is wet pyrolysis. What we usually are referring most commonly as wet pyrolysis is the hydrothermal carbonization process. And this is what we will talk about in the next few minutes. So what happened when I actually arrived also in Lesbos, what happened is that we had, of course, we had biomass and we could potentially pursue conventional pyrolysis, but we had a lot of liquid biowaste, and this biowaste come from the olive mills and from the dairy industry, but also from the alcohol production industry. Just to give you a reference, every hour that the olive mills are operating in Lesbos Island, they produce more than 100 tons of olive mill wastewater. And throughout the year, we know that we have more than 26,000 cubic meters of cheese whey that comes from the dairy production. And so we have a lot of waste that we were trying to figure out how we could use thermochemical processes to process and do something with them. The issue is that we have a lot of water content, and we need to exert a lot of energy in order to dry the material, in order to go with the conventional pathway that most of you are aware of, the pyrolysis, the combustion, the gasification process. And the idea was, okay, we wanted to take advantage of this water content and not to exert a lot of energy, spend a lot of energy to take it away. So the question was, what can we do? And the answer, like it's in most cases, in most technologies, is that comes from the earth itself. So what we did is we tried to emulate what's happening underground. So what's happening underground? We have the dead organic matter that goes deeper and deeper below the earth, and by means of high temperature and pressure, we have the organic matter gradually converting into high quality fuels. So here you see characteristically the conversion of organic matter into peat, brown coal, and then eventually to bituminous coal. So you have, as time goes by and the increase of heat and pressure, we have the increase also in the quality of the produced fuel. So this happens in a lot of million years, and we don't really want you to wait 1 million years. I mean, when you come to see the pilot plant, we'll not tell you that you have to wait that long. We usually do it in reactors that do it much faster, in a matter of hours. So the main idea is what you see here in the middle of the screen is a hydrothermal autoclave. It's technically a glorified pressure cooker that we put things inside. We have a high pressure, usually above 30 bars, most likely until 70 bars in the case of carbonization, intermediate temperatures between 180 and 250 degrees Celsius, but usually we see also processes that take place up to 300 degrees Celsius. And the idea is that we can take organic matter and we can gradually convert it by means of the presence of water into a carbonous product that we usually refer to as hydrochar, you see here on the right. And at the same time, what I want to point out is that this is a thermochemical process, and when we're talking about thermochemical process, we always have a thermochemical equilibrium. So we always will have a little bit of gaseous products and a little bit of liquid products. And by the way we are adjusting the temperature and the pressure and the retention time of the process, we are able to have a different set of products. So this is one in the right side of the slide. You see some applications that someone can actually do with hydrochar. Use it as solid fuel. It has some similar fuel properties like lignite. We can use it as soil amendment. This is something that we discussed a lot during the evolution of this proposal for this project. But also by upgrading it, we can also have other chemical applications as a filter absorbent. But this is a little bit more down the line than just using simply the hydrogen. And what really lies behind the operating process of this hydrothermal treatment is that the water itself changes its phase and it passes to subcritical and supercritical regimes. And the concept is not only that it becomes different in the enthalpy or in the phase. What is also an interesting part, and I would like to show you first this, is that as the temperature goes up, we have also other characteristics of water that change along with the temperature. And here you see how the dielectric constant changes, how the relative permittivity, as we commonly say it. So the thing is that when you start in the beginning in close to environment temperature, water has a relatively high dielectric constant. But if you go to higher temperatures, it comes into a level that behaves approximately like an organic solvent. And this changes the actual behavior of the water and how it affects the different thermochemical processes throughout hydrothermal treatment. And just to go back to the previous slide, what I told you before is that we're talking about a thermodynamic equilibrium. So in different regimes of enthalpy, we're getting a different set of products. What we are focusing now is on the lower part of this curve. As you see here is the hydrothermal carbonization with intermediate temperatures and pressures. If we go to more intense situations, we are able to produce bio-oil, and even further, what we actually are targeting as in the experimental stage here in the Laboratory of Energy Management to produce green hydrogen directly from liquid wastewater by switching to a supercritical water gasification regime. So I will not go, I will not analyze every single chemical process that happens here, but the basic idea is that in the beginning of the process, when we have slightly lower temperature, as we are heating up the reactor, we have the processes of hydrolysis and depolymerization taking place. And what does it do? It technically breaks down the bigger molecules into simpler molecules. So, for example, we will have the proteins and the polysaccharides, cracking down to disaccharides and monosaccharides or oligomers and amino acids. And this is the first stage. And then we have a lot of different pathways that the products can follow. So on the one side, we have the effect of deamination, and we have the production of organic acids. As you see here, they are in the middle of the screen. And some of them, they are the volatile fatty acids, some of them are a little bit heavier. And the concept is that they affect a lot the pH value of the material. And on the other side, we have when we have higher temperatures and when we reach to an intense enthalpy regime, then we have other processes that take place like cyclization and recondensation that are mainly the reason why we have the aromatization processes, the production of aromatic clusters and cyclic aromatics. And this is the initial stage before having the final polymerization stage, as you see here on the right side, for the production of polyaromatic structure char. And this is a product that is very close to what we refer as hydrochar. So this aspect of polymerization is not understood 100%. And if you have patience and maybe if you want to contact with me, I can provide you one of our recent studies that has utilizing a model which is called three-step evolution model that describes for the first time how hydrochar is being produced in the process of hydrothermal carbonization. So what happens with hydrothermal carbonization in real life is we have this liquid waste that you see here on your screen, but if you see also myself who have this liquid waste also here with me, and by doing this process of hydrothermal carbonization, we produce this liquid, solid and gas product. Here you see the liquid and the solid part, and by drying, we are able to produce this dry char here that you see in my hands, which is the material that we refer as hydrochar. So the question is how much do we retrieve from the initial content? So on the right side of this slide, you see the hydrochar yield in respect to the total solids that were as feedstock in the process, and this bars here that you can see here on the left side of the slide refer to the heating value of this material. So according to the different type of input, we get of course, different characteristics, but we usually see a product that has approximately 20 to 22 megajoules per kilo of heating value, and we always recover approximately 40 to 45% of the initial total solids. And you see below all the different references that maybe you can have a look later in order to see more details about our work. So a tricky part is that, as I told you before, it's a thermodynamic equilibrium with a lot of different products, and the idea is that, okay, of course, sometimes we get what we want, but sometimes we also get some products that we cannot necessarily deal with easily. So in the case of hydrothermal carbonization, we also have some liquid fractions that have a lot of liquid hydrocarbons that in some cases we need to deal with before having the final product for use. And of course, this project is not about hydrothermal carbonization. Mostly, it's about PFAS, and the idea is what's really the use of hydrothermal carbonization in respect of PFAS and mainly PFAS removal. And some recent studies have shown that by using moderate to high temperature in respect of the process of hydrothermal carbonization, have a decent removal efficiency. This is unfortunately the one part of the story, because of course we see some very good removal efficiency in some cases, but as you see, for example, from study number 3, we have in some other cases low removal efficiency. So the mixture of PFAS, for example, that somebody can choose can be critical for the success or the failure of the experiment. And what we have seen also, and what Nasos, as our leader here in the University of Aegean, will show you in the next meeting, is that we have some cases that we have PFAS that we can easily remove with hydrothermal carbonization, but on the other side we have other, for example, mesodiazoles that are not really removed with this process. So the thing is, we have to think how we can go further. And the main idea, and what we have seen in the literature, is that there are two ways that you can go in respect of the pH. And I would like to discuss first this slide, and then I will go back to the previous one. So the one idea is to go in lower pH acidic, let's say, conditions, and the other idea will go to alkaline conditions. So the low pH conditions, they do have a strong effect on the transformation of PFOA. But the thing is that they crack down these molecules into shorter chain PFAS, exactly as Hans-Peter was discussing with me in one of the previous meetings. One of the results of this study that I am sourcing here is that if you keep control the pH to 6 or 8, in some cases you are able to have an effect of the PFAS removal at some degree, not great results, but you are removing them. But at the same time, you don't have this short chain PFAS. When we have a very, very low pH conditions, like for example in this study was 3, the decided pH value, and then you have also this shorter chain PFAS that we find when we try to detect afterwards the PFAS. On the other side, we have the alkaline treatment that degrade PFAS in aqueous film forming foam. This is something that has been shown in the literature, but what is very wisely put by the author here is that the information is lacking regarding the treatment of PFAS in actual groundwater and soil. So this is something that is at the moment something that we would be very happy to look into in the upcoming studies. So also what we need to take into consideration is that we have phase transformations during the hydrothermal treatment, and maybe we have some carryover effect on the gaseous phase, but also we need to take into account the surface and the adhesive forces of hydrochar, and maybe some adhesion of PFAS on the surface of this material. Just to go back very fast, in respect of the hydrothermal alkaline reaction, which seems to be very interesting, is that we see that it has a very good effect, and actually Wang et al. Described the exact mechanism, because we had a conversation in the previous meeting, what's the mechanism of destroying the PFOA by hydrothermal treatment, and please refer to this slide, whoever is interested to have a look. And I promised you to show you the reactor. I think Dimitris is here. So before we start the reactor, I don't know if you can hear the video.
Begin laser ignition sequence.
Begin laser ignition!
I will stop sharing, and please, if you want, you can maximize my screen, and we can go very close here to see the hydrothermal reactor. We can, as you see here, it's already open, and we have filled in the sample, and we will now elevate the reactor. In order to close it, as you see, there is a continuous steering system. Okay, great. And if you hear me, I don't know if you can hear me, but from this side, we are doing the feeding. It's a continuous system where we can use this liquid prepared for feeding. And on the other side, we have the condenser of the instrument in order to recover the liquid and the gaseous products. So this was the main part of the presentation. I would like to thank you very much for your attention, and we're all waste management guys. So I really like this quote from George Miller during the movie Mad Max. So I will leave you with this, and thank you for your kind attention.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.